evaluation of the estimators. In the section before, we talk about obtained estimators, but the question is which estimator is optimal. First, we should define some property of the optimal estimators. The optimal estimator is the estimator which is closer to the parameters. This means the distance between estimator and parameters is minimum. One of popular criteria is the use of mean square error, and the optimal estimator is the estimator which is minimum mean square error. So in this part we tried to find estimator which minimum mean square error. First, we define the mean square error, the criteria of the mean square. Let the x1 to xn be a sample from fx and tx estimator of 2 theta. The mean square error measure the average square difference between tx and 2 theta, which the definition is presented here. The mean square error tx of a parameter 2 theta is defined by expectation tx minus 2 theta square. So if the distance between tx and 2 theta is large, the value of is mean square is bigger, and if tx is equal to theta, the mean square is equal to 0. Therefore, it is the best criteria to define the optimality of the estimator tx. But if you look at the definition of the mean square error, you can write it as done. You can add it expectation tx and minus expectation tx, and we can find square of the part 1 plus square of part 2 plus 2 square of the multiple of 2 parts. That one. So if you look at these expectation tx minus expectation tx and tx minus theta, because the expectation tx minus theta is not depend of x, so we have this form, and if you look of these is equal to that value which is 0, and the product is equal to 0, then the mean square error theta is equal this one, which is variance of tx, and that one because is square of bias, which bias define expectation tx minus 2 theta. So we want find the estimated tx which make mean square error of tx minimum. So we should find estimator which variance is minimum and bias is minimum. But actually they aren't estimator which both of them is minimum. So we define a restricted class. One of the restricted class is a class of the unbiased estimator. It means the bias of tx or expectation tx minus 2 theta is 0, or expectation Tx is 2 theta. Therefore we define the unbiased estimator. If x is a random variable with distribution f estimator Tx is an unbiased estimator of 2 theta if expectation of Tx is equal to 2 theta. So in this case the bias is equal to 0 and the mean square error is equal to variance of Tx. So the minimum of mean square error is equal to minimum of variance. We can see let x1 to xn be from normal mu sigma square. This is a theta is 2 dimension. If we define x bar as this and s do, we can find expectation x bar is mu and expectation square is sigma square. So x bar and s2 are the unbiased estimator of mu and sigma square respectively. In some cases we can find general form of the unbiased estimators. Is the benefit of the unbiased estimators. Let x be observation from fx equal b theta hx exponential theta x actually is exponential family. If h is differentiable, then expectation minus h prime hx is equal to theta. So in this in the exponential family of distribution, always you can have unbiased estimator for theta which defined by that. The proof is very simple. We can calculate of these estimators. You can find here, and by definition has this one and emitted h1 hx from by hx. You can have that one, and which is equal to this one, which is equal to 0. So in the exponential family we can find the unbiased estimator of theta, and here said example 4.3 we said for some other estimator, for example uniform distribution, which fx theta is equal to g theta function of theta and function of x, when the x the bound of x is depend of the theta, we can find differential. We can find estimate of g theta. For gamma theta, when gamma theta is differentiable. For the show this the proof, you can find the expectation Tx is equal g theta integral from 0 to theta Tx hx dx is equal gamma theta, and we have this one. If we take derivative, the differential or derivative from both sides of equation 3.1, we can find t theta h theta equal rho on the rho theta is differential of the gamma theta on the g theta, and so Tx is this one. If you want to check if Tx is the unbiased estimate of gamma theta, we can calculate the expectation of the tx, the expectation of tx is, then by the definition of expectation, is the value of tx on the density of x, and we have simplifying the expectation is equal to gamma theta, so the tx is the unbiased estimator of the gamma theta. So in the exponential family and in the uniform family, we can find the unbiased estimators. Okay, but in some cases we haven't unbiased estimator for all function of theta, only for some function. For example, let's say x1 to xn be a random sample from the Poisson, then g theta has unbiased estimator if g theta is the power 3 in theta. For the find this function, let g theta be a parameter we want to find the unbiased estimator of that, and which call it tx. So in this case it is satisfied if and only if we have these four. This is the expectation of the tx, and if you look of that, we can find this power 3 of theta is the power 3 of theta, e power n theta is power 3 of theta, therefore the g theta should be a power 3 of theta. And sometimes the unbiased estimate does not exist. For example, if x is a distribution as a binomial NOP, and we want to find the unbiased estimator of 1 over p, if there is an unbiased estimator of g p, we should have this one equation. And if you look after that, if p tends to 0, gp tends to infinity, and that the left side is tends to 0, t0. Therefore we haven't Disember, because the t0 is a finite function, but the right side is infinite and infinite. So for 1 over p does not exist unbiased estimator. However, we can find some estimators which is closed to 1 over p, because the xn is the closest to p, expectation of xn is p, and some xn is the unbiased estimator of p. We want to select it n over x is the near, the closest 1p, only with adjustment for x equals 0, because if you put x equals 0, this ratio is infinity. So and sometimes the unbiased estimator is misleading in meaningless estimators. For example, here we have truncated Poisson in 0. Okay, if you want to find the estimator, unbiased estimator for gamma theta equal to 1 minus p power minus theta, suppose tx is the unbiased estimator, but you have this equation, and that one is here. If you write this form, we can have this power series. So this power series is equal to that one, and therefore tx should be equal to 0 if x is odd and 2 is even. So is meaningless, because the 1 minus e power minus theta is a number between 0 and 1, but the ambas estimator said 0 and 2, which is not in the this interval. We can find the ambas estimator which is not belong to interval which define gamma theta. So this example we said yes is ambas estimator is the good estimators for many as of distribution, and what type of the function we can find the ambas estimator, but sometimes it is meaningless, sometimes there isn't any ambas estimators. In fact, we want to say the property of the ambas estimator by this example. No, as we find in the class the ambas estimator, the bias of the tx is equal to 0 and the mean square error is equal to variance of x. So the best estimator in the ambas class is the estimator which is which have a minimum variance or uniform minimum variance, which call it or UMVUE, and we said the definition if x is a random variable having the distribution fx, and we said the gamma theta is estimable if there exists the statistics ux such that expectation ux is the gamma theta. So we call a function gamma theta estimable if there is an ambas estimator. So in next let's ux is the UMVUE of the gamma theta if is the unbiased, and for other estimator tx of gamma theta the variance of ux is less than variance of tx. So the UMVUE estimator is the unbiased estimator which has uniformly minimum variance. In this section, in the contents of this section, we want to find the ambas estimator theta. Actually, the ambas estimator UMVUE is the optimal estimator in the ambas class. The first technique is the define a lower bound B theta for variance of the ambas estimators. So if we find T star such that the variance is T star is equal to bound of the variance of ambas estimator, so we the tx as the minimum variance, and it is UMVUE. This lower bound is called lower Kramer-Rao lower bound estimation. For this for Kramer-Rao lower bound we defined let x be a random variable from density function fx. It should be some open interval in R, it means that the theta is the one number, is not the vector, and Tx, suppose Tx is estimator of 2 theta, and some regularity condition is satisfied. First, the derivative of fx with respect to theta exists, and the derivative of integral hx fx theta is equal to hx, no, derivative of fx. It means we can put the derivative into integral. And 3 condition is the expectation round theta ln fx theta square is finite. So there are mean theorem here. We said is expectation t is a 2 theta equal plus b theta, and a conditional 1 to 3 is satisfied, then the variance of t is greater than this lower bound. This lower bound called the Kramer-Rowe lower bound. For the proof, if the expectation round theta ln fx square is infinity, denominator is infinity, so this ratio is equal to 0, which is always satisfied because the variance is the positive number. So for this condition, this lower bound inequality is satisfied. Therefore we assume expectation round theta ln fx square less than infinity. In this case we have expectation t equal to 2 theta plus b theta, and by definition has this integral. So we differentiable both sides with respect to theta, and we have round theta expectation t is equal of that one. By the conditional 2 we have that one, and we can write this product as this, because we showed this part before. Show that you know with the expectation of the round theta fx ln fx equals 0, and this expectation is equal to covariance of tx and round theta ln fx, because the covariance is the expectation of product of this one minus expectation that tx on the expectation round theta ln fx, but this expectation is equal to 0, so that the product is equal to covariance. And round theta, therefore the round theta is a square is equal to covariance square, and which is the Cauchy-Schwarz inequality. We say this is the less than variance of t on the variance or on theta ln fx, and the second part, and because the expectation is 0, we have variance t on the expectation of this part, and if you divided both part by this expectation, we find this lower one for the variance of the t. So if variance of the t, if 2 theta is tx is the unbiased estimator, so that b is the unbiased. If t is the unbiased estimator, b theta of bias is equal to 0. In this case we have this lower bound for the unbiased estimators. Actually, if 2 theta is equal to theta, the derivative of theta respect to theta is 1 and has this form of inequality. If Tx in addition is unbiased, then the variance of Tx is greater than 1 over expectation on theta ln fx square. If x is a vector of the random variable, which is IID, independent identical distribution, so that the distribution of f is the product of the distribution x1 to xn, and the expectation rho over rho theta ln fx square is n type of this one, which is called the Fisher information, and we can put this value in the denominator of inequality. So, and sometimes we can use of this equality or equations, we can show this one is equal by this one. Sometimes calculated this expectation is very easier than that one, and we can use of these equations. For example, let's x1 to xn be a random sample from the Poisson distribution. We want to find the Kramer lower one for the parameter gamma 1 theta equal theta and gamma 2 theta equal e minus theta. In this case we have, this is density function and this is the log of this density function. We calculate the derivative and the expectation of that one square. We have, if you put here, we can find that one, because the expectation x minus theta square is the variance of x, because x is the unbiased estimator of theta, and we can write as that one is 1 over theta, and the gamma 1 theta is theta, derivative of gamma 1 theta is equal 1. The Kramer row lower one is equal, that one is equal to theta over n, which is the variance of x bar. So the x bar has the x bar is the unbiased estimator of theta, and the variance of x bar is the is equal to lower bound of Kramer row. So for every unbiased estimator of theta has variance greater than variance of the x bar, so that the x bar is the UMVUE of the gamma 1 theta. In the case the gamma 2 is equal to e minus power minus theta, we have that one is a derivative, and if you put of the inequality, the lower one is equal of this one, which is theta e power minus 2 theta. The UMVUE in this case we can use the Kramer row, and we should calculate the UMVUE of this in this function in the next section. And the second example is the x is 1 x1 to n random sample from binary. The Kramer row lower bound for the gamma theta 1 theta is theta and gamma 2 theta is theta 1 I minus theta, and it has this is a distribution density function is the ln or log of distribution function, and we can calculate the derivative of the ln log of this density function. We have that one, and if you consider gamma 1 theta, the derivative is 1 and the lower bound is that one, which is the variance, but against the variance x bar, so that the x bar is the UMVU equal to gamma 1 theta. If the gamma theta is theta on 1 minus minus theta, which is variance of x, this is the derivative of the gamma 2 theta, and which is the lower bound of variance of the unbiased estimator of gamma 2 theta, and the next section we want the UMV for the gamma theta by the Kramer row lower bound. We can find the UMVUE for the theta on the 1 minus theta. So we define the mean square in this section, and we define the Kramer lower bound, the condition for the Kramer lower bound, and next part we talk about the property of the Kramer lower bound for finding the UMVUE for the parameter.